Hey guys, this video is the second part of designing distributed cache. This video covers very important topics in the distributed system design, and I would ask you to watch this video till end. I also have a challenge design question in this video, and I would like to see how many of you can actually solve this challenge design question. So in the previous video, we discussed what is a distributed cache, what are the different read-write policies in distributed cache, what are the different eviction policies for a cache, and we also discussed the functional and non-functional requirements of distributed cache. If you have not seen that video, you can watch this video here. Now we will design the distributed cache based on the functional and non-functional requirements that we discussed in that video. In the very simplest design, the distributed cache consists of a single server which uses a hash table to store the key value record. The lookup to the hash table is a constant time lookup, that is O1 complexity. Since in the requirements we decided to use least recently used eviction policy, so we will actually implement this distributed cache with a hash table and a double linked list as follows. The hash table contains the keys and the pointer to the nodes in the double linked list as the values for those keys. When an insert key value happens, it creates a node. Insert that node at the head of the double linked list and insert the pointer to that node in the hash table against the key. So the insertion to the cache is a constant time operation, that is O1 complexity, because insertion at the head of the node is a constant time operation. Also the insertion in a map is also has O1 complexity. O1 complexity. So now let's suppose an insertion happen here for the record B. You can see now that the cache now contains two records, a key A with its value and a record that was inserted after A at the head of the double linked list, which is B. Now let's add some more records into the cache. So now we have inserted 4 records in this cache. Let's assume that the maximum size of this cache is 4. So now let's see what happens when a read request comes. So let's suppose we receive a get call for the key C. So first we will look into the hash table for this C. It's a constant time complexity operation, so O1 complexity operation. From the lookup we will get the pointer in the double linked list. Now what we will do, we will actually take out this node from the double linked list and we will move this node at the head. In order to implement the least recently used operation, we will always, whenever we are inserting a node in the cache, we will always add it at the head, or whenever we access a node in this cache, we will always move it from its current position to the head of the double linked list. So let's suppose we access C. So after accessing the C, this double linked list will become something like this. So now you can see that C is now at the head or in the double linked list. Now suppose we get a read request for the key A. Then first we will look up here in the hash table, constant time lookup, which is O1. We go here, we remove this node, move it to the head of the double linked list and return whatever the value of the A to the caller. So after this access, that is accessing A, this double linked list will look like this. So you can see now that A is now at the head of the double linked list. Now let's suppose an insertion call comes for some key E, which is not here in the cache. In that case, since the maximum size of the cache is 4 in our example here, we need to evict an entry. And what we will do here in that case, we will actually evict the last entry D, because this is the least recently used entry. We will remove this entry and then we will insert the next entry E at the head. So after this double linked list will look like this. So you can see now that E is now at the head of the double linked list and the previous entry, the least recently used entry, that is D, is gone now. Now I have a design challenge for you. Let me know the answer in the comment below, and if you are unable to figure out the answer, still comment below if you are interested to know about the answer. If I get 10 comments in the next 1 week, I will then make a separate video for the solution of this design challenge. So the challenge question is that since there will be multiple, like hundreds or thousands of read or write calls will be coming to this cache. So it means every time an insert happen or a get happen, we will be actually either inserting some records in the distribute cache or here in the double linked list. Or if it's a get request, we will be moving some nodes in the double linked list to the head. And in that case, if there are multiple requests coming in parallel, it means multiple threads are accessing this data structure. We need to synchronize all these calls or all these access to these data structures. The one easiest mechanism to implement this synchronization is to have a global lock. So anytime a read or write request come, we acquire a global lock and then we access these data structures. But the problem with the global lock is that all the access to this cache is now serialized. This is very inefficient implementation of the cache. So my question is for you is, what are the other possible implementation of locks or other synchronization mechanism that we can use to do insert or retrieve items from this cache which does not have adverse effect on the performance of the cache? Also think about it that if you are implementing this cache in languages like Java or C#, you may not have to worry about deallocating the memory of these nodes. But let's suppose if you are implementing this cache in C or C++, where you are also responsible for freeing the memory of the node, how will you manage everything? So you can see in this implementation where we are using only a single server, using this hash table and a double linked list implementation, we can actually fulfill all the functional requirements. Like we can insert keys in the bucket, we can get keys, we can delete keys. We are also using the least recently used eviction policy. So this implementation fulfill all the functional requirements. However, as far as the non-functional requirements are concerned, this implementation does not fulfill many of them. For example, if we are using only a single server, then this implementation is not fault tolerant and highly available. The single server can go down at any point in time. Also, this implementation is not scalable with the increasing load. A single server maybe can serve up to 10,000 or 20,000 requests per second. But what about if the load increases to 100,000 requests per second or million requests per second? So we see that this implementation is neither highly available nor scalable. Although this implementation does serve the consistency requirement and is also affordable because we are just using a single server, but not being highly available and scalable are enough for us to look for other possible design architectures. However, we don't need to discard this design. Instead, what we can do is that we can actually improve upon this design by introducing more servers in our cache architecture. Now there are two approaches to actually increase the number of servers. In the first approach, we introduce more servers to the store. So these servers that we introduce are called replicas of the first server because they store exactly the same copy of key value data. This would improve the read performance and will also improve the availability requirement to some extent. However, the maximum size of the cache will remain same. It also means that it does not solve the scalability requirements for the cache if we need a larger size cache. In the second approach, we divide the whole key range into several partitions or shards, where each partition is stored in a separate server. Suppose we have a key range from 0x00 to 0xff. We can divide this whole key range into 4 different partitions from 0x00 to 0x3f, which we can store in one server S1. Then from 0x40 to 0x7f in a second server S2. From 0x80 to 0xbf in a third server S3. And from 0xc0 to 0xff in a fourth server S4. So in this way, we can actually partition a whole key range into different small partitions or shards, where each partition or shard can be on a different server. We use both approaches to design the distributed cache. First, we divide the whole cache into multiple partitions or shards. So let's, as an example, we have divided the whole cache into 10 partitions in this example. The goal of partitioning is to spread the data and the query load evenly across several nodes or servers. So in theory, if every node takes a fair share, then if there are 10 partitions in the cache, then they should be able to handle 10 times as much data, also 10 times the read-write throughput. Now we can partition this key value data by two approaches. The first approach is partition by key range. In this approach, we partition the data based on the key. Example, let's suppose we have a cache where the key is the name of a user and the value is the user information. We can partition data into, let's say, 26 partitions, where one partition will store all the records of users whose name starts with letter A. The second partition will store all the records of users whose name starts with letter B, and so on. In this approach, the keys may not be necessarily evenly spread because the data may not be evenly distributed. Also, if you consider our previous example in which we designed tiny URL service, for which you can find the video here, you remember that we were actually creating short URL in the format 0001, 0002, 0003, and so on. It means that we will be writing or reading from the same partition all the time, which nullifies the whole purpose of using different partitions. Although this approach is good for certain scenarios that we will encounter in future videos, however, the most popular approach is the second approach. The second approach is partition by hash of key. In this approach, we use the hash of the key and then we use the hash value to determine the partition. A good hash function makes sure that all the data is uniformly distributed among all the partitions. Once you have a good hash function for keys, you can assign each partition a different range of hashes, and a key value is stored in the partition having the hash range where its hash lies. So we can scale the distributed cache by increasing the number of partitions. However, if each partition is just a single server or replica, then it means each partition itself is not fault tolerant and it's not highly available. In that case, we can increase the number of replicas in the partition to at least 2 nodes or more, and in that case now we have different approaches. So now let's take a very simple example. We are assuming that each partition has 2 replicas. So one of them is basically primary replica and other is secondary replica. This is a primary replica, this is a secondary replica. This is the primary replica and this is the secondary replica. When we have 2 or more replicas in a partition, there are different approaches that we can use to actually do writes to these partitions. So these are the different approaches that we can use to write to a partition when the partition has 2 or more nodes. I'm not going to detail of these right now. We can discuss them in some future video in more detail. But right now, I will just introduce them to you in a single sentences. So in a single master or single leader, there will be one primary or master node or master replica. All the writes will go to the primary replica, and the primary replica will be responsible for determining the order of writes. For example, if multiple writes came at the same time, the primary replica will be responsible for determining which order will go first and which writes will go first and which writes will go second, and so on. So all the writes will go to the primary replica in case of a single master or leader. So this primary replica or the master replica will then replicate or copy the data to the secondary or slave replicas. In a multi-master or multi-leader approach, there could be 2 or more masters in the partition, and the writes can go to any of those masters, and those master nodes are then responsible for replicating or copying the data to all the other nodes in the partition. And the third approach is leaderless approach, in which the writes can go to any node in the partition. So in this video, I'm not going to discuss the differences between these approaches in detail and what are the pros and cons of each approach. Maybe in some future video I will discuss these, and if you are interested to know about this, please let me know in the comment below. Right now in our design, we are using the single master or single leader approach. And so now let's go back to our design. Suppose we have these partitions, and each partition have two replicas. One is the primary replica, other is the secondary replica. And now all the writes goes to the primary replica, and then primary replica copy the writes to the secondary or slave replica. Now I have a question for you. You can pause the video for some time to think about it. Let me know, when a write happened to primary replica, whether the primary replica copy the data to the slave or secondary replica synchronously or asynchronously. So you can pause the video right now here, think about it and let me know. So what do you think, whether the data is copied synchronously or asynchronously by the primary replica? The right answer is it depends. It depends on the overall scenario for which you are using the distributed cache. If the overall scenario dictates that the data in the cache is only inserted and never gets updated, then you can actually do copy from primary to secondary replica in asynchronously. In that case, what will happen? Let's say some write happen, and primary is now copying data to the secondary, no replica in asynchronously in the background. But let's suppose primary dies. It means that the secondary replica will actually lose some writes to the cache in this partition. What would be the side effect in that case? Side effect would be, when you try to access the data will not be present in the cache, so it will result in a cache miss, which will then cause your application servers to go and retrieve the data from the data store. So when the data is in this case, when the data is being copied to the secondary in a asynchronous manner, this secondary replica is in standby mode. It is never used for reading. It only gets promoted to primary when the primary dies, but for the normal reading we will never use this secondary. Why? Because this secondary would be lagging behind the primary, since all the writes to the secondary are happening asynchronously. And since we have a non-functional requirement that we would like our data to be strongly consistent, we cannot read from these secondary servers. Now in a separate scenario where the data in the cache can also be updated at any point in time, we cannot copy the data from the primary to the secondary replica asynchronously. The reason is that, let's suppose you have some data in the cache, and then an update call happen, which actually update the same record in the cache. And now if that record has not been yet copied to the secondary and the primary dies, it means the secondary has some stale data, which will again break our strong consistency non-functional requirement. So in that scenario, if the overall scenario for the service dictates that there could be updates that could happen in the distributed cache, in that case all the copy operation from the primary to the secondary, they execute synchronously. So whenever an insert or update happens, inside the same update call we synchronously copy the data to the secondary replicas. However, the side effect of this approach is that now if the secondary server is down, or if there is a network partition between the primary and the secondary replica, that is, they are unable to communicate over the network, then the write availability will be affected, because now as soon as a write comes and if you cannot copy data synchronously to the secondary because the secondary is down or there is a network partition, then you will not be able to mark that write as successful. Problem. This is the classical cap theorem problem. So here in this case, in case of a network partition between the primary and the secondary, you can either achieve high availability or you can achieve consistency, strong consistency, but you cannot achieve both. So we can actually avoid that unavailability by introducing one more secondary replica in this design. So now let's suppose instead of 2 replicas, we have 3 replicas, 1 primary, 2 secondary. And so now in this case, we can actually make sure that we are able to read and write to the partitions by using this formula. Where n is the total number of replicas in a partition, which is in this case is 3. R is the number of replicas from which we have to read the data in order to mark the read as successful, and W is the number of replicas where we have to write the data to mark the write as successful. So let's see what will happen in this scenario now. So in our case, now each partition has 3 number of nodes. So whenever an insert or write happen, if we can write to at least 2 nodes, we can say the write is successful. So let's say the write happens, a write call comes to the primary, if the primary then write to itself, and it send the write request to these secondary servers. As soon as 2 of the servers, including the primary server, say that the write is successful, the primary server can mark the write as successful. And now in that case, for strong consistency, if we need to read data, we need to read data from at least 2 nodes. And let's see example. The example is that let's suppose a write happened for a key A. The primary was able to write here and here, but somehow the write to this server get delayed. But since primary was able to write to these 2 servers, the write was marked as successful. Now when a read request comes, then the read needs to go to at least 2 of the servers. So it's totally possible the read could go to these 2 servers or these 2 servers. If it goes to these 2 servers or these 2 servers, this server will say it doesn't have the data, but this server will say that it has the data, and so the read will still be successful. So this is the formula that we usually use in case of read write. If we want to avoid unavailability, but we also want to perform reads and writes with strong consistency. Now we will design our distributed cache with whatever we have discussed so far. It is a good idea to start with a large number of partitions in the beginning, so that if you have to further divide a partition into sub-partitions, the amount of data moved between the partitions is minimum. So we will start with 1000 partitions in the very beginning. And please note, these 1000 partitions are just logical partitions. They are not physical server or nodes. Each partition will have 3 replicas. So in total we will have 3000 replicas. Again, please note, these 3000 replicas are just logical replicas. They are not physical server or nodes. So now these 3000 replicas will be empty in the beginning because there is no data in the cache. So these 3000 replicas can be actually mapped to 3 physical servers to minimize the cost. Now as the size of the partition is increased, as we are inserting different keys into the partition, then we can eventually introduce more physical nodes or server in the design, and then we can move around those partitions or replicas which exist in the initial 3 servers to those new servers. Thus the information about the number of partitions, the range of hash keys, which each partition map, the number of replicas in each partition, what are the primary and the secondary replicas in each partition, and what are the physical servers or node to which these replicas are mapped. All this information is called topology information. So this information will be stored in the topology manager. The topology manager is responsible for configuring different attributes of the topology of distributed cache. What are different attributes? Number of partitions, number of replicas in each partition, the primary and secondary replicas, the range of hash keys which each partition serve, etc., etc. Now there are two mechanisms by which the application servers in a service can access the distributed cache. In the first mechanism, the application server directly talks with the topology manager to get the information about the partitions, their ranges of hash keys, and also their replicas. And then the application server, after talking to topology manager, then talks directly to the partition in order to insert or retrieve some key value record. Also, when writing, the application server directly sends the write request to the primary replica of a partition where it needs to insert the key, and the application server also reads from, let's say, 2 replicas here in order to read from the cache. The application servers achieve all the above by using the SDK. So the SDK has all the implementation code. It talks to the topology manager. The SDK also do the writes by talking to the primary replica in each partition, and it also reads by reading from 2 replicas in each partition. I personally does not prefer this approach, because now this SDK is a thick client SDK, and now any feature work or bug fix require updating this SDK at the client side, which is not controlled by the team which owns the distributed cache. This adds additional friction to shipping code and features, and adds additional complexity to the feature design, because now you have to think about backward compatibility with the older SDKs, because a client may not update the SDK regularly. The other approach that I prefer is to have a thin SDK client with minimal implementation that is needed for implementing get, insert, or delete APIs. Now the SDK talks to a routing layer through the load balancer. The routing layer will have at least like minimum 3 number of servers, but we can increase the number of routing servers as the load increases on the distributed cache. Now these routing servers talks to topology manager directly. So whenever some update to topology happen, what is the update to topology? Either we introduce a new partition by splitting a partition, or we merge 2 partitions into one, or we introduce a new replica in a partition, or remove a replica from the partition, or the primary replica switches and becomes secondary, and some secondary replica promoted to primary replica in a partition. All these changes are called topology update. So whenever a topology update happens, the topology manager actually send all the updates to all these routing servers. So you can see that topology manager is a sort of coordinating component here in the distributed cache. Usually topology manager can be implemented using Zookeeper as well. Now the application servers only talk to this routing layer through the load balancer, and then these routing servers know which partition to talk based on the topology whenever an insert or read or delete command comes from the client. So when a client or application server calls the insert API, the insert call will come to one of the routing server. Based on the topology, the routing server will know, okay, to which partition it needs to write, and it will also know what is the primary replica of that partition. So the routing server will actually redirect the insert call to that primary replica of a partition. In case of read, the routing server first determine which partition to read from based on the key, and then send the read request to 2 replicas in that partition. This is the overall design of distributed cache. We have routing layer, we have topology manager, and we have different partitions. So I'm going to stop the video here. This topic of partition and replicas is so big that I can make several videos on it. There are other things which I haven't also discussed. For example, how a partition is split into 2 or more partitions, or how a partition gets, like how 2 or more partitions merge together to form a single partition. What happens when there is a topology update is happening? So what happens to read and write requests when a topology update is happening? For example, when a primary dies and a secondary takes over as a primary, or whenever we are splitting a partition, what happens to the writes happening to those partitions? So these we can actually discuss in further videos if there's an interest for it. So if you are interested for me to make more videos on this topic, then please comment below. Also let me know if you also let me know in the comments below if you like this video, and also please like